Greetings and welcome to this presentation of the final project report for structural fire engineering and design of filled composite plate shear walls, also referred to as Speedcore. This report is published and available in the public domain from the Charles Pankow Foundation. There is also a website that AISC, the American Institute of Steel Construction, maintains for the Speedcore project, that also has links to this final project report for download. The sponsors for this project include the Charles Pankow Foundation, the Steel Institute of New York, and the American Institute of Steel Construction. The project team was led by myself. My name is Amit Varma. I am a professor in the School of Civil Engineering at Purdue University. My team included the PhD student Taghipour, the postdoctoral researcher Dr. Saahas Bhardwaj, and my master's student Preshit Wazalwar. To begin the discussion, composite plate shear walls are being used in commercial construction due to the potential benefits of schedule contraction and the extent of modularity available during construction. For example, on the left-hand side, you're seeing a high-rise 22-story steel structure designed using coupled composite plate shear walls as the core, the elevator core of the structure. When you look closely at figure B, you notice that the elevator cores are made of composite plate shear walls that are connected together by coupling beams. These coupling beams are also composite members, in this case, concrete-filled rectangular tubes. The walls themselves consist of two steel plates that are located on the exterior surfaces, and the steel plates are connected using tie bars. This steel module can be prefabricated in the shop, shipped to the site, assembled, and then filled with concrete. There is no need for any additional reinforcing bars or rebars in this type of construction. Generally, composite action can be achieved between the steel plates and the concrete infill just by using the tie bars. Sometimes additional shear studs can be used in order to reduce the number of ties. On the right-hand side, you're seeing a photograph that is taken of the Rainier Square project located in downtown Seattle. This structure uses the composite plate shear walls for its design. You're noticing the composite plate shear walls and the coupling beams that form the elevator core in the photograph. What you'll also notice are some concrete-filled tube columns that are located closer to the edges of the frame structure. Overall, this system achieves the modularity, where the steel modules of the walls and the columns are prefabricated in the shop, shipped to the site, assembled, and then filled with concrete. When constructing this structure, generally about 4 stories of the core wall are constructed ahead, and then the concrete is filled in the walls, the columns, and also the floor system about at the same time. As you can notice, composite plate shear walls are extremely useful for achieving schedule contraction through modularity of fabrication and construction. However, one of the biggest questions that arises is associated with the fire resistance of the system. The reason being the steel plates are directly exposed to fire conditions because they're located on the exterior surfaces. Generally, in reinforced concrete, the steel rebars are located within the concrete and thus protected somewhat from direct fire exposure. But in these composite walls, the steel plates are directly exposed to fire conditions, which will lead to elevated temperature of the steel and elevated temperature in the concrete. But because the concrete has a lower thermal conductivity, this will lead to a nonlinear thermal gradient through the wall thickness, where the temperatures in the concrete will be much lower than the temperature of the steel plate on the surface. The elevated temperatures will degrade the steel elastic modulus and the yield strength, and also the concrete closer to the steel plates will be experiencing higher temperatures and degraded material properties. The focus of this project is to conduct experimental investigations and numerical studies to evaluate the stability response, the strength, and behavior of these composite plate shear walls under fire loading. Besides the walls, we will also be looking at concrete filled tube columns, and the focus will be on developing tools, design tools, analysis tools, and prescriptive methods also for fire resistant design. It's important to note that our approach here consists of conducting some experimental investigations and validating a numerical modeling approach. Once the numerical modeling approach is benchmarked, we use it to conduct detailed parametric studies and develop design provisions. The expected results from the project include experimental results, data, photographs, findings, and observations of these composite plate shear walls under fire loading. Fire resistance and design tools for both concrete filled tube columns and composite plate shear walls. Also some simple strength degradation design equations that can be used, and also fire resistance rating that can be used along with prescriptive provisions for these systems. Finally, the project will also develop some benchmark finite element models that people can continue to use in the future for performance-based design evaluations. So the way we've set up this presentation is that it has 6 modules. The first module focuses on the background and the heating program, the design of the experiment. I'll talk a little bit about that in this current presentation. Next will be Module 1, which will talk about the experimental investigations that were conducted in the laboratory using specimens that we had built. The second module will focus on the development and benchmarking of numerical models, in general 3D finite element models. The third module will focus on conducting parametric studies using these benchmark numerical models. Various material and geometric parameters will be looked at, including slenderness, thickness, load ratio, etc. The fourth module will focus on concrete filled tubes, the composite columns, and their parametric studies. The fifth module will consist of looking at vent holes, the design of vent holes for the system, in particular vent holes for relieving the steam that is generated as these specimens, as these walls, composite walls and columns are heated. And the final module will present the summary and conclusions for the overall project. I'll be presenting Module 0 and Module 6. My PhD student, Taghipour, will be presenting Modules 1, 2, and 3. The master student, Preshit, will be presenting Module 4, and our postdoc, Dr. Bhardwaj, will be presenting Module 5. So you will get to hear from all the authors of that document. So let's get started with Module 0, which focuses on the background and the heating program for this particular investigation. What we are going to do is look at some of the test data that is available in the literature, and then we're going to talk about developing the experimental method for our particular test. The previous study was conducted by Wei et al. In 2017. We found in the literature there's not a lot of testing that has been conducted on composite plate shear walls. But there was a study that was conducted in China that was published in 2017. We're going to take a look at their test matrix. We're going to look at their test setup, some of the failure modes that they've reported, and we'll learn from their investigation. That will help us design our experimental evaluation. Next, we'll take a look at the ceramic fiber radiant heaters that we will be using for conducting our tests in Bowen Laboratory. Finally, in this module, we'll look at some trial fire tests and compare some of the temperature time curves that we obtained from a real furnace test to those obtained from tests conducted using ceramic fiber radiant heaters. This is the test matrix of the study conducted by Wei et al. That was published in 2017. What you'll notice from this test matrix is that there were about 8 specimens that were subjected to uniform fire tests. And there were about 4 specimens that were subjected to one-sided fire tests. Generally, the wall thicknesses were in the range of about 150 millimeters, which is about 6 inches, to 200 millimeters, which is about 8 inches. What you'll also notice is that most of the specimens, almost 10 out of the 12 reported here, had a wall thickness of 150 millimeters or 6 inches. The heights of the specimens varied from about 850 millimeters to 1,850 millimeters. Most of the specimens were tested at heights of 850 millimeters or 1,000 millimeters. This results in a wall slenderness ratio, that is wall height divided by wall thickness ratio, of about 4 to 12. What you'll also notice is that a lot of these tests were conducted at a load ratio of about 34% with respect to the section axial load capacity. In general, the load ratios varied from about 26% to 40%, but most of the tests were conducted at 34%. This is a very high load ratio for a composite wall, which is generally not subjected to gravity loads that are going to be this high in a high-rise building. The steel plate thicknesses were typically from 3 millimeters to about 5 millimeters. There were several specimens that have 3 millimeter steel plates. There was one specimen with only 2 millimeters, and there were some with 5 millimeters. The tie bars in the specimens had a diameter of 10 millimeters and were spaced at 160 millimeters, and there were some shear studs that were 2 millimeters in diameter and generally at a spacing of about 40 millimeters. There were some specimens that had shear stud spacing of about 40 to 80 millimeters. The general steel reinforcement ratio varied from about 2.7 to 6.7%. And the fire scenarios, as I mentioned in the beginning, that were considered included all-sided and also single-sided fire tests. This matrix also includes some of the failure modes that were observed for these particular tests, where the initial LB stands for local buckling, WC stands for weld cracking, GI, and there was only one specimen with GI that had global instability. There were some one-sided specimens that had thermal insulation failure, and there were some specimens that had no failure at all. The fire resistance time in minutes is reported in this particular column, what you'll notice is that most of these times are greater than 120 minutes, and some of them are even close to or greater than 180 minutes. This slide shows the test setup that was used for conducting the experimental investigations in China. What you'll notice is that they are using a gas furnace in order to subject the specimens to heating. The specimen is subjected to gravity loading from top using this reaction frame and actuator that is applying the axial loading through a reinforced concrete loading beam. You're also seeing the base beam and the specimen located in between the two. A photograph on the right-hand side clarifies a little more the specimen, the distributing beams, which are also insulated, the walls of the furnace, and the actuator, which is located outside the furnace, being used to apply loading. And this loading is being spread using a distributing beam. Some of the failure modes that were observed during this test include, for example, local buckling. Extensive local buckling was observed in between the tie bars. This was associated with some shear stud failures in between the tie bars as well. Another failure mode that was observed was cracking of the welds at the corners between the flange plates and the web plates, the splitting failure. And another failure mode that was observed for one of the specimens was global instability, where the specimen H over TW, height over thickness, was slender enough that the specimen was undergoing overall global instability. These were some of the failure modes that were observed during the test in China. This slide summarizes some of the results that were obtained from the tests conducted in China. You're looking at the true thickness temperature profile for one of the specimens, SCW4. The y-axis is the temperature in degrees Celsius. The x-axis is the distance from the mid-thickness of the wall, where the mid-thickness of the wall is located at 0, you're seeing here, and the temperature is increasing to the exterior surface, and the temperature is increasing to the other surface as well. The wall surfaces are where the heating is being applied. We're looking at the temperature profile through the wall cross-section or the wall thickness at 30 minutes all the way up to 150 minutes. And you see how the temperature goes up on the surfaces but lags behind towards the center because of the low thermal conductivity of concrete. When the heating is applied on only one side, for example, in specimen SCW9, what you'll notice is that the unheated or unexposed wall surface has lower temperatures, whereas the heated wall surface has very high temperatures. You're looking at the temperature profile through the wall thickness as the time goes from 30 minutes all the way up to 240 minutes. And here you're looking at the axial displacement versus time curves for specimens 1 through 8 that were subjected to uniform heating. What you'll notice is that a lot of the axial displacement versus time curves are clumped around the same time interval of about 160 minutes, with the exception of one specimen that seems to have a behavior that's a little bit different, going all the way up to 240. We found from their test data that increasing wall slenderness ratio leads to global instability. And that's when the wall slenderness ratio becomes very large. They had that happen for just one specimen. Generally, they found some shear stud failures at weld locations, but this may be associated with how the shear studs were welded in their specimen designs. And the steel ratio was about 5% in their studies. Overall, this test data provides us with good experimental results to compare with to benchmark the numerical models and compare with the results from the numerical analysis. For the tests that we conducted at Bowen Laboratory, we did not use a gas furnace. We don't have a gas furnace at Bowen Laboratory, so we did not do the test like that. Instead, what we used are referred to as ceramic fiber radiant heaters. You're seeing some photographs of these heaters located on the left-hand side. There is no open flame or fire in this particular type of testing. Instead, these heaters radiate the heat from their surfaces directly to the surface of the specimen. We can attach thermocouples directly to the steel surfaces, and we can control the radiant heat output from these heaters using a computer program to achieve a specific temperature versus time curve on the steel surface. We can program and control the temperature of the steel going up and also as it cools down to a certain extent. These heaters are readily available in the US market. They are manufactured by the Watlow Electric Manufacturing Company. We have various varieties and shapes and sizes of these heaters in Bowen Laboratory. For example, we have heaters that are 16 inches wide by about 36 inches long. We also have heaters that are only 8 inches wide by about 36 inches long. So there's a different size and shape in which these are available. What's important to note is that each heater is controlled individually, which means that we can have different temperature zones along the length or in different parts of the specimen as we wish. Of course, in this case, we applied uniform temperature, but each heater can be controlled individually for applying a specific temperature time curve on the surface of the steel. Here's a close-up picture showing you again what the surface of the heater looks like. What you'll notice are those metal coils. Electricity is passed through these coils. This is a heater that uses electricity. It doesn't use gas or fuel. These high temperature elements, because of their internal resistance, become very hot, and then they radiate the heat from these electrical coils onto the surface of the steel. We take the ceramic fiber heater and we have placed it in some metal cases so that they are a little more sturdy, robust, and easy to move around. That's the electrical power supply that we have provided, and each heater has its own individual thermocouple that goes into the control cabinet. So each heater gets its power and its temperature is controlled by the cabinet using a PID controller, and that's why you see so many PID controllers on the surfaces. And these PID controllers are then connected to a computer program, a spec view that we use to individually control each of the heaters. We provide the temperature that they want to go up, that we are asking them to go up to, and we can control the temperature versus time history specifically. Without getting into too many details, here I'm showing you the results of our trial thermal tests. What I'm showing you here are temperature time curves on the surface of the steel plates of the composite plate shear walls. You'll notice that the dotted lines that I'm showing you are coming from the ceramic fiber radiant heaters that we used in our laboratory. And the solid lines, for at least two of them, are coming from the tests conducted by Wei et al. On the composite plate shear walls. I've also added a few lines from furnace tests conducted and available in the literature by different researchers. What all these plots show is that the typical temperature versus time curve that we obtain by using the ceramic fiber radiant heaters is quite comparable to the surface temperature time curves that one would obtain in a full furnace test, in a gas furnace test, as shown here from the various other researchers. This is quite significant because the real temperature time histories that we are interested in are those on the steel surface. In all of these tests, the goal was to approach the ISO 834 temperature time curve. So when Wei et al. Did their experiments, they controlled the furnace to follow the ISO 834 temperature time curve. But what we are looking at here is the steel surface temperature time curve that they obtained. It's important to note that the ISO curve is a gas temperature time curve, not that of the surface. So for the unprotected specimen, the surface temperature time curves compares really well with the ceramic fiber radiant heater provided steel surface temperature time curve. The difference between the two heating approaches is that our heaters directly control the steel surface temperature time curve, whereas the furnace tests control the gas temperature, and from that we get the steel surface time temperature curve. Overall, this shows that the test method that we are going to use is quite comparable, and it's going to result in surface temperature time histories for the composite plate shear walls that is very comparable to that you would obtain from conducting a gas furnace test. Additional details of this, comparisons and discussions are provided in the report. This brings us to the end of Module 0. And the next, we're going to start looking at the results from the experimental investigations we conducted on these composite plate shear walls in Module 1.